Hi everyone, and welcome back to the Forum for Learning and to part 5 of lecture 2 in the Biology 101 lecture series. In this video, we're going to talk about these 4 things. So we're going to talk about what hydrogen bonds are, what hydrophilic and hydrophobic interactions are, what van der Waals forces are, and we'll finish off the video by talking about how these different bonding types and different intra and intramolecular forces compare in terms of bond strength. So without further ado, let's get started. Alright, so let's talk about hydrogen bonding. So hydrogen bonding is not a form of bonding, but rather an intramolecular or intermolecular force of attraction that takes place when hydrogen is bonded to oxygen, fluorine, or nitrogen through a polar covalent bond. So let's break that down, and let's write that down, right? So first and foremost, it's not a bond. Despite the term, hydrogen bonding, it is not a form of bonding, and it's not a bond in the way that covalent bonds are bonds and ionic bonds are bonds, right? But what it is it's a hydrogen bonding is an intramolecular or intermolecular force of attraction. And intra means within a molecule, inter means between molecules, right? So between, and intra means within. Okay, and these, this force of attraction only takes place when hydrogen is bonded to oxygen, fluorine, or nitrogen through a polar covalent bond. So what that means is hydrogen bonding only occurs when hydrogen is bonded, and it's through a polar covalent bond, is bonded to fluorine, oxygen, and nitrogen. A good way to remember is FON, right? The acronym FON: fluorine, oxygen, nitrogen. And so that's what hydrogen bonding is. Now I know that was a lot of jargon, so let's look at an example and really go through and explain what hydrogen bonding is. Alright, so for this example, we'll talk about how hydrogen bonding takes place in water. All right, so H bonding in water. Okay, now we used water as an example to talk about polar covalent bonds or polar covalent bonding in the previous video in part 4 of lecture 2. So if you guys want to get an overview of covalent bonds in general, and polar versus non-polar and all of that, I highly suggest you guys take a look at the previous video, part 4 of lecture 2, before you guys review this video. But anyway, so let's look at this. So in that video we discussed how water and the structure of water is determined by its polar covalent bonds, right? So water is, we said, H2O. So we have a hydrogen molecule bonded to a central oxygen bonded to another hydrogen molecule, right? Now, we discussed in that video that in this molecule of water, we have 2 polar covalent bonds, right? And both of them are oxygen-hydrogen polar covalent bonds. And so what happens? So we discussed kind of in a polar covalent bond, there is a sort of what happens is the atom with the higher electronegativity will draw electron density, or will draw the bonding pair of electrons closer to itself and away from the atom with lower electronegativity, right? So in this case, oxygen is our atom with the higher electronegativity, and hydrogen is the atom with the lower electronegativity. So what happens is oxygen will have or the bonding pair of electrons in this bond here and in this bond here will be located closer to the oxygen's nucleus than the hydrogen's nucleus. And so what that means is this negative electron density, right, because electrons are inherently negatively charged, so the electron density is located closer to oxygen and further away from hydrogen. So what that's going to do is it's going to induce what's called polarity. So we're going to have the oxygen atom, because again the electrons are located closer to, or the bonding electrons are located closer to the oxygen's nucleus, is going to have a net or a partial negative charge, whereas because these bonding electrons are located further away from the hydrogen's nucleus, hydrogen will have a partial positive charge. Now remember, we it's known that opposite charges will attract each other, right? So positive attracts negative, negative attracts positive. Now, in this case here, we discussed two properties of covalent bonds in part 4 of lecture 2, and those two properties were that the length of the covalent bond cannot change and the bond angle doesn't change, right? And so what that means is we can't have attraction between this oxygen or this partial negative and this partial positive here, right? Because these things can't get closer or further away because the bond length is it can't be changed. And so what happens? So how does that attraction? Because remember we said that it's an intra or intermolecular force of attraction, this hydrogen bonding. So how does that work? Well, we can't have it, within this molecule, right? Because this bond cannot change, and these atoms cannot get closer, and cannot attract one another. But what can happen is that, say in a glass of water, there's millions of molecules of water, right? So what happens when you add in another molecule of water? Well, say we have hydrogen here, which is oriented a different way, and a hydrogen here, right? Now here we have this hydrogen also has a partial positive charge, this hydrogen has a partial positive charge, this oxygen has a partial negative charge. So now if you look, what happens? This negative charge is in close proximity with this positive charge, or positive partial charge of hydrogen, right? So these two partial charges will begin to attract each other, just like these two partial charges over here would begin to attract each other. And so this attraction between the partial positive of one molecule and partial negative of another molecule is what's called a hydrogen bond. So as you can see, it's not a physical bond like these two covalent bonds are, right? Or like this covalent bond or this covalent bond. It's not a physical bond, but rather it's a force of attraction between molecules that have polar covalent bonds, as these are polar covalent bonds, right? Now the caveat to hydrogen bonding is that they only form when there's a polar covalent bond between hydrogen and, like we said, fluorine, oxygen, or nitrogen. In other words, between hydrogen and a highly electronegative atom. So why is that? Well, first of all, so let's first write that down, right? So we said it only occurs when hydrogen is bonded to this via a polar covalent bond, right? So why is that? So why is this? So let's first answer let's first answer why does it have to be a polar covalent bond, right? Why can't it be, a nonpolar covalent or like an ionic bond or whatever, right? And the reason is because, so let's write this down. So the reason is because hydrogen bonding is, again, we explained, is a mere attraction between opposing partial charges. So in order for a hydrogen bond to form, you need to have strong enough partial charges, which can only occur in polar covalent bonds, right? Because nonpolar covalent bonds inherently have very weak sort of separation of charge across that bond, right? Because, like we said, the electronegativity difference between atoms in a nonpolar covalent bond is less than 0.5. So that means that the difference is very low, which means that the one atom doesn't significantly pull the bonding electrons more than the other atom, right? They share fairly equally, and so the partial charges aren't that strong, right? Because their separation is not that strong because there's equal sharing. But so that's why it has to be a polar covalent bond, because a polar covalent bond, there's the difference in electronegativity between the two atoms involved in that bond is greater than 0.5, or between 0.5 and 1.5, right? And so that's why it has to be between, hydrogen has to be bonded via a polar covalent bond to hydrogen, oxygen, fluorine, oxygen, or nitrogen. So now let's answer why doesn't hydrogen have to be bonded to those three in order to have hydrogen bonding? Well, that's because fluorine, oxygen, and nitrogen, they have very high electronegativities. And so what that means is the difference in electronegativity between fluorine and hydrogen, or oxygen and hydrogen, or nitrogen and hydrogen are pretty high, right? And so what that means is that there's a greater separation of charge. And if there's a greater separation of charge, the stronger those charges are, right? So let's reiterate that. So say in this water molecule, we have hydrogen bonded to an oxygen, right? So pretend it's like a tug of war, right? So you pretend, say, you have a rope and you have two individuals on that rope. Now, if one individual is significantly stronger than the other, what happens? There's a greater pull of that rope, right, by the stronger person, and more of that rope will be closer or will be in the hands of the stronger person than the weaker person. So in this case, the strength is equivalent to electronegativity, right? In this case, so oxygen has a significantly higher electronegativity than hydrogen, and the differences are at something around like 1.4. And so because of that, oxygen will pull a greater portion of those bonding electrons, or that electron density, towards itself, right? Which means that more of that negative charge is focused closer to oxygen. Now, the stronger that atom is, right, that's doing the pulling, the greater that atom will have the partial negative charge, the stronger that partial negative is going to be, right, and vice versa. So the weaker the atom that is in the bond where the electrons are getting pulled away from, the more positive that partial charge is going to be, right? So the greater that difference in electronegativity between the two atoms in a bond, the stronger that partial charge is going to be on either atom, right? So in this case, oxygen is partial negative, hydrogen is a partial positive. And that's why, and greater separation means greater strength of these partial charges, right? This partial charge is going to be very strong, as is this partial charge on this hydrogen, and vice versa, right? And so what that means is, because there's a greater strength in those charges, the greater the attractive force, right, between, say, this partial negative and this partial positive of this hydrogen, right? The stronger this more positive this is, and the more negative this is, the stronger this attraction is, right? And so that's why, in order for hydrogen bonding, or this attractive force, to occur, that hydrogen has to be bonded to one of these really highly electronegative atoms. Okay, so again, just to kind of go over this again, hydrogen bonding is not a bond, right? It's not a bond like covalent bonding or ionic bonding, but rather it's an intermolecular or intramolecular force of attraction. Like we said, in this case, it's intermolecular, right? It's between two molecules of water, and it only occurs when hydrogen is bonded to a highly electronegative atom like fluorine, oxygen, and nitrogen. If hydrogen is bonded to another atom, say, that's not one of those, the electronegativity difference isn't strong enough to generate those really strong partial charges to then elicit those strong forces of attraction. And again, to reiterate, hydrogen bonding is an intermolecular force or intramolecular force, right, of attraction. And so the strength of that is nowhere near covalent bonds or ionic bonds. But we'll get to that later in this video, where we talk about bond strengths across different types of bonds and different types of inter and intramolecular forces. So that's hydrogen bonding. So now let's talk about what are hydrophilic or hydrophobic interaction. Okay, so let's talk about hydrophilic and hydrophobic interactions. Now, before we discuss hydrophilic and hydrophobic interactions, there's something that I want to kind of discuss. So we mentioned in the previous section, talking about hydrogen bonding, we discussed that hydrogen bonding occurs when hydrogen is bonded to fluorine, oxygen, or nitrogen, right? And this hydrogen bonding, this attractive force, is a result of hydrogen being bonded to a really electronegative atom, and the delta electronegativity between those two atoms being really great as a result of that, and that causes there to be relatively strong partial charges across the polar covalent bond, and those partial charges result in attractive forces between molecules or within molecules, right? Intra or intermolecular. But what happens when hydrogen is bonded to another atom outside of fluorine, oxygen, nitrogen? Say hydrogen is bonded to bromine, for example, right? There is still a significant enough difference in electronegativity to where there will still be partial charges across the atoms on that polar covalent bond, right? But they're just not going to be as strong of partial charges as if hydrogen was bonded to oxygen, fluorine, or nitrogen, because bromine is not as electronegative as those three atoms, right? So just because in order for hydrogen bonding to happen, need hydrogen to be bonded to fluorine, oxygen, or nitrogen, that doesn't mean that there can't be partial charges or the presence of partial charges if hydrogen is bonded to any other atom, right? So basically, what that means is that just like water molecules can hydrogen bond with other water molecules, right? Because the force of attraction is there because those partial charges are relatively strong because, again, hydrogen is bonded to a really, one of 3 really highly electronegative atoms. Polar molecules, so polar molecules could be, say, for example, bromine bonded to hydrogen, right? Because they're still polar, but they're not as polar as, hydrogen bonded to oxygen, fluorine, or nitrogen. But so just like water molecules can hydrogen bond with other water molecules, polar molecules can interact with other polar molecules through the weak attractive forces of opposing partial charges, right? And so it's very similar to hydrogen bonding, but it's just not as strong as the attractive force amongst these opposing partial charges are not going to be as strong as those present during hydrogen bonding, right? Or in hydrogen bonding. Okay. So now that we got that out of the way, so we said water, can hydrogen bond with water, but polar molecules can also interact with polar molecules. And they're not going to be hydrogen bonding, right? Because you're not having as strong partial charges, but there's still interactions or still attractive forces from those opposing partial charges, despite them being not as strong as hydrogen bonding. Now we'll get to bond strength and all that in a little bit, but I just wanted to give that caveat that, it's not just water that can form attractive forces amongst other water molecules, right? It could be any other polar molecule can interact with any other polar molecule, and water is polar, right? We established that already. Okay, so with that distinction, let's talk about hydrophilic and hydrophobic interactions. So what is that? Well, hydrophilic and hydrophobic interactions basically dictate, or they basically they're basically how molecules interact specifically with water, right? They just describe how molecules interact specifically with water. So hydrophobic and hydrophilic interactions, they basically describe how molecules interact specifically with water, right? And so let's discuss hydrophilic interactions first. So hydrophilic interactions, so if we hydrophilic interactions. So hydrophilic interactions are the result of, or they describe how polar molecules interact with water, right? So let's break this down. So hydro obviously means water. Philic, right, kind of means loving or liking, right? So basically it's kind of just the suffix anyway. So hydrophilic interactions are essentially water-loving interactions. And so what that means is that, polar molecules can interact with water. And so, and again, the reason that polar molecules can interact with water are because of those, is because of the weak attractive forces due to those opposing partial charges. Okay, so hydrophilic interactions they describe how polar molecules interact with water. Right, and polar molecules love water because water is also another polar molecule, and there's partial charges across both of those kinds of molecules, right? Because any polar molecule is going to have partial charge. Water obviously has partial charges, and so there's going to be an attractive force that's present, which is why polar molecules are water loving, or these interactions are called hydrophilic, and they're water loving. And so and the idea is that the hydrophilic interactions are kind of very similar to the mechanism of hydrogen bonding, but just with other atoms, and not just with hydrogen bonded to fluorine, oxygen, or nitrogen. It could be any other polar molecule, but then the kind of the nature of the attractive force is the same, just not the strength. But we'll talk about bond strength a little bit later. Okay, so now what happens when we have nonpolar molecules, right? How do nonpolar molecules interact with water? Well, we said initially that polar molecules will interact well with other polar molecules. And just like that, nonpolar molecules will interact with other nonpolar molecules, right? So, and that's why these are called, so what are hydrophobic interactions? So hydrophobic interactions, well, if you break down hydrophobic, hydro is again water, right? The prefix for water. Phobic is fear, right? So hydrophobic interactions are interactions between water and a molecule that's water fearing. So they basically describe how nonpolar molecules interact with water, right? So we said that polar molecules, will interact with other polar molecules through those weak attractive forces due to the opposing partial charges. And when polar molecules interact with water, it's called a hydrophilic interaction, right? Because polar molecules are water-loving due to their similarity in partial charges, and can obviously, and as a result, can attract water molecules, or water molecules can attract polar molecules, and vice versa. And the opposite happens for nonpolar molecules, right? Nonpolar molecules will interact with other nonpolar molecules. And so nonpolar molecules are again hydrophobic because they're water and they're water fearing. So how do hydrophobic interactions, we discussed hydrophilic interactions are, they occur through those attractive forces, right? So they attract one another, and it's very similar mechanism to hydrogen bonding, just not as strong. But hydrophobic interactions are a little bit different. So when nonpolar molecules interact with water, what happens is that these nonpolar molecules will aggregate together and water will surround them. And the reason is because nonpolar molecules can only form very weak interactions, right? Because nonpolar molecules don't have a large enough difference in electronegativity between the atoms in a nonpolar bond to then cause the presence of partial charges, right? And the partial charges are really what cause that the attractive forces. And so in a nonpolar bond, you don't have that much of, you have equal sharing of electrons, right? You don't have a disparity in the way electrons are shared because electronegativities of the two atoms involved are fairly close to each other. So you have fairly equal sharing of those electrons, which means you don't have partial charges, and so they can't really form, they can't really have strong attractions or interactions with other charged molecules, right? So, or molecules with partial charges. So the reason is again because nonpolar molecules can only form weak interactions, and so these interactions are much weaker, obviously, than hydrogen bonds because there's no partial charges involved in this case. And because they're much weaker than the hydrogen bonds that water molecules can form amongst themselves, what's going to happen is that you're going to have all of these nonpolar molecules, or they're going to aggregate together, they're going to come close to each other, and water will surround them. And the reason that happens is because it's easier for water to interact with itself, because water is polar, and polar will interact with polar, than it is for water to interact with these nonpolar molecules. And it's a lot easier for these nonpolar molecules to interact with other nonpolar molecules than with polar molecules such as water. So it's just easier from a physics standpoint for water to just to form a sphere, and for these nonpolar molecules to aggregate in the center. So let's write that. So what happens is, so in this case, what happens is that the nonpolar molecules will aggregate together in the center, and water will surround them. Right? So there's really no specific interaction between nonpolar molecules and water, right? It's mostly interaction between nonpolar molecules who aggregate together and an interaction between the water molecules that surround this aggregate. Okay, and so that's really hydrophilic and hydrophobic interactions in a nutshell. So the main takeaway here is that polar molecules can interact with other polar molecules. Nonpolar molecules will tend to interact with other nonpolar molecules. And this is just hydrophilic and hydrophobic interactions. So what's next? Let's see. So what are van der Waals forces? Okay, so let's talk about van der Waals. Alright, so let's talk about van der Waals forces. So what are van der Waals forces? So van der Waals forces are very weak partial charges that develop that are highly transient and brief, right? So van der Waals forces are very weak partial charges that do arise in molecules, and these van der Waals forces, or these weak partial charges, are transient or brief, or they exist only for a brief amount of time, right? So how does this work? Well, so what happens is, so when two nonpolar molecules come in close contact, the random electron distribution in one molecule at a given moment will cause an opposite charge distribution in the other molecule because of the repulsive forces between electrons. Okay, so and the result of that, because again you have the result of this distribution and this repulsion of electrons is a very brief and weak charge separation, and that results in weak and again brief partial positive, partial negative charges that then attract each other. And this weak and brief attractive force is called van der Waals. So let's look at an example, right? Let's look at two bromine molecules, right? Because so, it's an example. Let's take up two bromine molecules, right? So we have one bromine molecule, and we have, we'll draw the other one later. Okay, so there's electrons here, right? So, and the bonding pair of electrons. Now, within this bromine molecule, the electrons can be all over the place, right? They're constantly in motion. They're not 100% stationary, right? They're always moving right, within those orbitals of either bromine. So you might have a situation where, for example, like in a split moment, you have, say, all of the electrons, so all 12 here, 1, 2, 3, 4, say 5, 6, 7, 8, 9, and then we have 10, 11, and 12, right? So let's say that this is the distribution at a given moment in time, right? It's like a split second, maybe even a millisecond. So now what happens? Well, all of the electrons are located on this side of the atom, and so now this side is going to slightly have a partial negative charge, right? Again, it's very brief. It's a split second situation, and this side of the bromine is going to have a partial positive, right? Because there's less electron density there. It's mostly located here, so this entire bromine molecule will have a slight negative pole or partial charge here on this side of on this bromine side of the molecule, and a partial positive on that side. So now what happens? Say another bromine and bromine molecule will come, right? So let's say we have a bromine here, and we'll draw it this way, right? So now what happens? So again, this is the molecule, right? So what happens is, well, because this partial negative charge and due to the electrons that are kind of focused around here or concentrated around here, is going to drive all of the electrons of this to this side, right? So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then say 10, 11, 12 or something like that. So now what happens is for this molecule, this side of the bromine molecule is going to have a partial negative charge, and this side is going to have a partial positive charge. And so what happens is, because of the random distribution of electrons in one molecule, right, at a split second, right, just a specific instantaneous time, that's going to induce sort of a charge on the other end because of the repulsive forces of these electrons and these electrons, right? You're not going to have two electrons here and electrons here, because if you have electrons here, like that's the current state that this bromine molecule is in, it's going to drive whatever's next to it, the electrons in the molecule that's next to it is going to be driven in a certain way where the electrons are going to be forced to the other side because of the repulsive forces, right? Because it's two negatives, and so they're not going to want to be next to each other. So they're going to go here, and that's going to induce a partial positive charge on this end and a partial negative charge on this end. And this bromine atom will do the same for another bromine atom, and then so on or molecule, and so on and so forth. Right. So now these partial charges, again, very brief, very instantaneous, will begin to attract. There's a certain degree of attraction between these two partial charges, just like we saw in polar molecules, right? And so, again, the important thing is that they're very brief and they're very transient, because these electrons are only going to be here for like a split second, and they're going to navigate to the other side of the molecule, and it's all random distribution. And so this is what's called a van der Waals force, right? It's that weak and brief attractive force that results from these partial charges that result from just a random orientation of electrons in one molecule, and how that affects the distribution of electrons in the other due to repulsive forces. And then you have some sort of the net result is a brief and really weak and transient attractive force between these two molecules. Now, the important thing to note is that for van der Waals, van der Waals forces can occur in both polar and nonpolar molecules. So, can occur in both polar and nonpolar molecules, right? Because it just has to do with just the random distribution of electrons at a given moment in time. But the important thing is that it can happen in both polar and non-polar molecules. But with respect to van der Waals forces, the van der Waals forces are the only type of intermolecular forces found in nonpolar molecules. So they can occur in both polar and nonpolar molecules, but they are the only type of intermolecular forces found in nonpolar molecules. So in nonpolar molecules, the only intermolecular force that's going to be present is going to be these van der Waals forces. All right? Cool. Okay, so that was van der Waals forces, so what's left? So now let's talk about how different bonding types and different inter and intramolecular forces compare in terms of bond strength and how they interact with each other. All right, so let's get started on that. All right, so now let's talk about bond interactions and bond strength, right? So let's first talk about bond interactions. Okay, so we'll talk about sort of how polar bonds or polar molecules and nonpolar molecules interact with one another. So polar molecules will interact with other polar molecules, including water, because water is a polar molecule, right? So the other polar molecules and ionic molecules and anionic molecules. Okay, so polar molecules will interact with other polar molecules and ionic molecules. So let's look at a few examples to kind of talk about, how that interaction happens. And first of all, the reason polar molecules can interact with other polar molecules and ionic molecules is the fact that is a result of the opposite partial charges found across polar covalent bonds, right? So the difference in electronegativity between the two atoms in the polar covalent bond will give rise to partial positive and negative charges across that polar covalent bond, and there will be, and those charges it could be intramolecularly or intermolecularly, will attract other molecules or other atoms within the same molecule due to those partial charges. Okay, so let's talk about. So we'll first talk about polar molecule with polar molecule, right? So how does that happen? So we'll look at hydrogen chloride, right? So hydrogen chloride is HCl, and chlorine is significantly more electronegative than hydrogen is, right? So chlorine is going to draw a majority of the bonding pair of electrons across this bond towards its nucleus and away from the hydrogen nucleus. So chlorine is going to have a partial negative charge, and it's going to also result in hydrogen having a partial positive charge, right? Because the electron density from the bonding electron pair is being drawn towards chlorine and away from the hydrogen atom. So now we have partial charges across that polar covalent bond. And so say we have, another hydrogen chloride molecule, right? So we have another HCl, and the same situation arises here. Across this polar covalent bond, majority of those bonding electrons are going to be located closer to the chlorine nucleus or chloride nucleus because of its greater electronegativity, and so it's going to have a partial negative charge. Again, those electrons are going to be away from the hydrogen atom, so it's going to be a partial positive charge. And so you have these partial charges that exist across polar covalent bonds. Now, what happens? Well, now what happens is this partial negative charge on chlorine will be attracted to this partial positive charge on the hydrogen atom, right? And so now there is some level of attraction, right? Some sort of an attractive force. And so this is how polar molecules will interact with other polar molecules. Now, we discussed another way polar molecules can interact with other polar molecules through hydrogen bonding, specifically with water, right? So we discussed here, where's hydrogen bonding? Right here. So we have, it's a little kind of jank, but we can see. So we have one water molecule here, another water molecule here, and we have partial charges on that oxygen, and this oxygen partial negative charges, because again, oxygen is the atom that has a greater electronegativity, so it's going to pull that bonding pair of electrons towards itself, giving it a partial negative charge, and hydrogen is going to receive a partial positive charge. And so we have the result of hydrogen bonding here, and obviously water is a polar molecule, so this is another form of polar molecules interacting with one another, specifically with water. So now let's talk about what happens when polar molecules interact with ionic molecules, right? So for that, I'll just paste something here. Okay, so let's talk about what's going on here, right? So in this example, we have sodium chloride, which is table salt, in water. So sodium chloride, that's our ionic molecule, and water is our polar molecule, right? So what happens? Well, what happens is when you put sodium chloride in water, it'll dissolve into its constituent ions of the positive sodium ion and the negative chlorine ion, right, or chloride ion. And so the partial negative pole in the water molecule, which the negative pole is going to in the water molecule is going to be at the end of the oxygen, right? Because remember, oxygen is the more electronegative atom. It's going to draw the bonding pair of electrons towards itself. It's going to have a partial negative charge. So what's going to happen is that the negative pole in the water molecule, so that negative pole in the water molecule is in the oxygen. Oxygen houses that negative pole, right, because of its electronegativity, is going to attract the positive sodium ion. So that's what's happening here. So you have the partially negative oxygen atom in the water molecule attracting the positive, or being attracted to the positive sodium ion, right? So it's this is a partial negative, this is a partial negative, this is a partial negative, and this is a partial negative. And so the negative charge will be attracted to the positive sodium ion. And on the flip side, the partial positive pole in water, which is, at the level of the hydrogen, so partial positive, partial positive, partial positive, partial positive, and so on, will be attracted to the negative charge in the chloride ion, right? So what happens is, again, the sodium chloride, you drop that in water, the actual physical compound of sodium chloride, it's going to dissociate into its constituents of, the positive sodium ion and the negative chloride ion, and water is going to sort of surround them and orient such that, the oxygen of the water molecule will attract the positive sodium ion, and the positive hydrogen atom within the water molecule will attract the negative chloride ion, right? And this attraction, what actually happens is, as you can see, there's some sort of shielding going on, right? Shielding of the ions, sodium and chloride ions, by water molecules. And so the attraction between water molecules and the constituent ions of sodium chloride will actually prevent the ions from reassociating into solid sodium chloride, because water is shielding it. Remember, in order for attraction to happen, it's based on two things, right? It's the strength of the charges, of the opposite charges. So the stronger the positive and negative charges are, the greater the attractive force. The other one is also the distance between those charges, right? So the further away this positive sodium is from this negative chloride, the weaker that attraction becomes, right? The weaker the attraction becomes, and there's no desire for them to reassociate back into sodium chloride. And the reason they don't is because the water surrounding it and kind of cutting off that charge, or the attraction between these two ions. Okay, so the net result is that water will actually prevent, or the attractive forces between the water molecules and the constituent ions of the sodium chloride will prevent those ions from reassociating into solid NaCl, or sodium chloride. So that's with respect to polar molecules, right? So we said overall polar molecules will interact with other polar molecules and ionic molecules, and water is included in that category of polar molecules. Okay, so what happens with respect to non-polar molecules? We talked a little bit about it before. So non-polar molecules. They'll tend to stick together with other nonpolar molecules, especially in the presence of water. So nonpolar molecules will interact / stick together with other nonpolar molecules, right? And especially this is the case when it's with respect to in the presence of water, and gives rise to hydrophobic interactions, right? We talked about this earlier, and we discussed that nonpolar molecules will aggregate together, and water will surround them, right? Because it's easier for water and more energetically favorable for water to hydrogen bond with itself than to try and interact with these nonpolar molecules, and vice versa. It's more energetically favorable for these nonpolar molecules to interact with themselves than with water, and so you end up having nonpolar molecules sticking together and interacting together with each other than with water or polar molecules. So the general rule here is that polar molecules will interact with polar molecules or ionic molecules, and nonpolar molecules will interact with other nonpolar molecules, right? And that gives rise to a big common theme throughout biology, and it's a statement, you guys have probably heard it before, is like dissolves like. And this is a huge theme across biology, because polar molecules will dissolve polar molecules, nonpolar molecules will dissolve or interact with other nonpolar molecules, right? And this is the basis of, we'll talk about this later, about like the cell membrane and all of that as we continue through this lecture series. So we talked about now bond interactions. So now let's talk about bond strength. Okay, so let's talk about bond strength. So the order of bond strength is covalent bond, followed by ionic bonds, followed by the hydrogen bond, followed by hydrophilic interactions, followed by hydrophobic interactions, followed by van der Waals forces. Okay, so let's discuss covalent and ionic bonds first, right? Because those are actual types of bonding, right? Hydrogen bonding, hydrophobic interactions, and van der Waals, those are just intermolecular forces of attraction, right? It's an important distinction to make. Whereas these are actual types of bonding, where you have either sharing of electrons or complete transfer of electrons. And this is with respect to, remember, it's in biological systems. That's the caveat, right? So this order applies to biological systems. So let's talk about covalent bonds. So covalent bonds are fairly strong, right? So covalent bonds are the strongest form of bonding. They're the strongest form of bonding in biological systems. Okay, so covalent bonds are the strongest bond when it comes to biological systems, and they're quite strong. Now, ionic bonds are quite interesting, and ionic bonds are interesting because with respect to the presence of ionic bonds in biological systems, they're not as strong as covalent bonds, but ionic bonds have higher theoretical bond strength than covalent bonds. So why is that, and what does that mean? Well, so the reason ionic bonds are strong, or have the higher theoretical bond strength, but are actually weaker than covalent bonds in biological systems, is because biological systems are water-based, right? We have 70% of the human body is water, and so biological systems are inherently, majority of that is water-based, and so what that means is that most ionic bonds in biological systems, or ionic compounds in biological systems, will be dissolved and not in their solid state, like we talked about with what happens with sodium chloride, right? Sodium chloride in biological systems is going to be like this. The sodium and the chloride ion are going to be separated because they're going to dissociate when in the presence of water, and water will be shielding them from each other, right? Excuse me. So because these ions are separated from one another and as a result further apart and shielded by the water molecules, the attraction between those ions is much weaker than when in the solid form, right? And so in biological systems, ionic bonds are not as strong as covalent bonds because, again, in biological systems, ionic compounds will have dissociated, and those charges between the two ions in an ionic bond will be weak because water will be shielding them, and due to the shielding and the separation of those two charges, the attractive force between those two and the desire to form an ionic bond again is going to be weak and low, right? But we did say that ionic bonds do have higher theoretical bond strengths, right? So let's write that down first, and we'll explain why. So they're weaker than covalent bonds in biological systems, right? But they do technically have higher theoretical bond strengths. So we said in the biological system, these ionic compounds will be dissociated, charge separation, water will shield them, and so they're going to be weaker than covalent bonds, right? Because the attractive force is not going to be as strong. Now, what happens when they're in the solid form? Well, when they're in the solid form, the ionic bond is much stronger than the covalent bond. And the reason for that is because in its solid form, the ions are much closer together. And if they're much closer together, they exert much greater attractive force on each other, right? Because we said two factors play a role in determining force of attraction. First one is the actual intensity of the charges involved in that force of attraction. And the other one is the distance. The closer they are, the greater the attractive force, right? Well, the actual charges themselves in an ionic bond are stronger, but in biological systems the distance is far greater because water shields it, and that's why ionic bonds in biological systems are weaker than covalent bonds. But when those ionic charges are within close proximity to each other, like they are when they're in the solid form, so outside of biological systems, what happens? Well, in those situations, ionic bonds are stronger than covalent bonds, right? And that's where that higher theoretical strength comes from with respect to ionic bonds. Okay, so that was ionic bonding and covalent bonding. So now let's talk about the intermolecular forces of attraction and how they compare in sort of the kind of, I guess, how they compare with respect to their forces of attraction. So the first one is hydrogen bonding. We discussed that earlier in this video. Now, hydrogen bonding is the strongest of the intra or intermolecular interactions, right? So it's the strongest in intra or intermolecular forces. Okay, so hydrogen bonding is the strongest of these right here, of these intermolecular forces here, but they're obviously weaker than something like ionic bonding or ionic attractions, right? And that's obviously because with respect to ionic attractions, those attractions arise from actual ions, right, where the intensity of the charge is far greater. Whereas for hydrogen bonding, it's attraction due to partial charges, the occurrence of partial charges when hydrogen obviously is bonded to either oxygen, fluorine, or nitrogen, right? So they are weaker than ionic attractions. Okay, and they're obviously much weaker than covalent bonds, because covalent bonds are actual bonds, and you actually have sharing of electrons, versus just being, hydrogen bonding strictly being just a form of an intermolecular force of attraction. So they're weaker than ionic attractions. They're also weaker than covalent bonds. And again, remember, the bond designation in hydrogen bond is a misnomer, right? It's misleading. It's not an actual bond. It's just a force of attraction. But it is the strongest force of attraction when it comes to intermolecular forces of attraction, or intra or inter. Okay, now a key thing to note is that even though hydrogen bonds are relatively weak by themselves, they can be considerably strong when there are many hydrogen bonds together, like in water, for example, right? All the water molecules can form hydrogen bonds with each other. So when you have, they're weak individually, but they're strong in number. Okay, so weak individually with respect to, say, covalent and ionic bonds, but strong together, right? And like, for example, in like water, a lot of water's chemical or physical properties rather come from the water's ability to hydrogen bond, and we'll get to that in the next lecture where we talk about water and its properties. Okay, so now let's talk about hydrophobic, hydrophilic interactions. So these guys are obviously, so hydrophilic interactions, there's still partial charges involved, right? Because hydrophilic interactions means they're water loving, which means they can interact with water, which means those molecules are going to have polar covalent bonds. Polar covalent bonds means that there's going to be a distribution of electrons across that bond, such that the atom with the higher electronegativity in that bond is going to have more of the bonding electron pairs, and the atom with the lower electronegativity is going to receive less of that, which means there's going to be partial charges across that. And if there's partial charges, that means there could be attractive forces present. But they're obviously not going to be as strong as hydrogen bonds, because remember, in hydrogen bonds, you have to have hydrogen covalently bonded to either fluorine, oxygen, or nitrogen, and those are the most electronegative atoms in the periodic table. And so the partial charges that arise from those bonds are going to be the greatest, which means the greatest partial charge means the greatest force of attraction, which is why hydrogen bonds are greater than hydrophilic interactions. But in hydrophilic interactions, you still have those partial charges, they're just not as strong, and so they're still an attractive force, okay, or force of attraction. Now we have hydrophobic interactions. So let's just write some stuff about hydrophilic, what we just discussed. So we still have partial charges, but weaker than H bonds, right? Now hydrophobic interactions are weaker still, right? And then we have van der Waals forces. So van der Waals forces are the weakest form of intra or intermolecular forces. But similar to hydrogen bonds, they're similar to hydrogen bonds in the way that they're quite weak individually, but they can be relatively strong when present in large numbers. So the same thing applies. So they're weak individually, but strong together. Obviously, they're much weaker than hydrogen bonds, but when they're present in large numbers, they can have a significant effect on the physical properties of an element or of a molecule. So that was bond strength, and let's see what else we have. Do we have anything else? Let's see. So we talked about what hydrogen bonds were. We talked about what hydrophilic and hydrophobic interactions were. We talked about van der Waals forces, and then we just finished talking about how different bonding types and intermolecular forces compare in terms of bond strength, as well as how they interact with each other. So that's it for part 5 of lecture 2. Thank you guys for watching. I hope you guys learned something. And until next time, okay, bye. Oh, forgot the most important part of the video. As always, stay true, be kind, and never stop learning. Alright, I'll catch you guys in the next one. Okay, bye.